Japan sits on the edge of disaster. Over 1,000 earthquakes strike each year, costing billions of dollars and crippling power for millions of people. So why are engineers betting on a concrete dam, not just to hold water, but to capture seismic chaos and turn it into clean electricity? If this works, everything we know about surviving earthquakes and powering cities could change. The real question is this: can harnessing earthquakes become our greatest energy breakthrough, or is it just a fantasy waiting to crack? Japan's position on the Pacific Ring of Fire means the ground never truly rests. Each year, the Japan Meteorological Agency records over 1,000 earthquakes strong enough to be felt. The actual number of seismic events climbs closer to 1,500. The country endures more quakes per square mile than almost anywhere else on Earth. For families and businesses, this constant motion is more than a nuisance. It is a relentless threat to homes, infrastructure, and the power that keeps cities alive. The financial toll is staggering. In 2011, the Tohoku earthquake and tsunami alone brought losses estimated at $210 billion, the highest ever recorded for a natural disaster. Every year, earthquakes and their aftershocks erase about $200 billion in value worldwide, and Japan shoulders a heavy share of that burden. Yet nearly all the mechanical energy unleashed by these quakes vanishes as heat, ground motion, and destruction. Little, if any, is captured or turned to use. Meanwhile, the same events that topple buildings and bridges also threaten the electrical grid. Hospitals, water pumps, and emergency centers depend on a steady flow of power, but disaster often means blackouts that can last for days or even weeks. With seismic risk this high and the costs mounting, the need for a new approach is not just academic. It is a matter of survival and stability for millions. When an earthquake strikes, the electric grid is often the first system to falter. Transmission towers buckle, high voltage lines snap, and substations go dark in seconds. In the aftermath of the 2011 disaster, entire neighborhoods in Sendai lost power for weeks. Hospitals switched to backup generators, rationing fuel as they treated waves of injured patients. Water pumps and sewage treatment plants ground to a halt, leaving families to queue for bottled water and basic supplies. Even the most advanced cities with their sprawling underground cables and redundant circuits found themselves vulnerable. Aftershocks made repairs dangerous, sometimes forcing utility crews to abandon their posts until the ground settled. In Tokyo, a single fault in a transformer triggered a cascading outage that left millions without lights or heat on a cold spring night. The blackout didn't just darken homes, it silenced emergency radio, stalled subway trains, and shut down vital data centers. Every hour without electricity meant greater risk for those trapped in elevators, reliant on medical devices, or cut off from emergency alerts. As the hours stretched into days, the city's dependence on a stable grid became painfully clear. Each blackout exposed not just the fragility of wires and concrete, but the reality that modern life can unravel in a heartbeat when the flow of power stops. In a country where seismic threats never sleep, The search for a way to capture and store that energy, rather than just brace for disaster, became more urgent than ever. Piezoelectric materials are at the heart of the idea to harvest energy from earthquakes. Two names dominate the field: PZT, lead zirconate titanate, and PVDF, a flexible polymer called polyvinylidene fluoride. Both materials have a special property. When squeezed or bent, they generate an electric charge. But what sets them apart is how they handle stress and how much power they can actually deliver. Durability is the practical limit with PZT. PZT is a ceramic. It is stiff, brittle, and produces a strong electrical response even under small strains. In the lab, PZT patches bonded to concrete beams have shown that just a few square centimeters can light an LED or power a wireless sensor. Under heavy vibration, a single PZT harvester can put out anywhere from a few milliwatts to several watts, enough for low-power electronics, but nowhere near grid scale. The catch is durability. PZT does not like to flex too much. Push it past its limits, and the ceramic can crack, losing its ability to generate power. PVDF is the more flexible option. PVDF, on the other hand, is a plastic film. It bends easily and survives much larger deformations without breaking. Its electrical output per unit strain is lower than PZT, but because it can flex more, PVDF can sometimes produce higher voltages during large, slow movements, the kind you might see in a dam during a quake. Engineers often embed PVDF strips in engineered cement composites, letting them ride out repeated cycles of bending and stretching. In repeated 4-point bending tests, PVDF films have survived thousands of cycles with little drop in performance, making them attractive for long-term, low-maintenance installations. The trade-off is clear. PZT delivers higher power in small, sharp doses, but needs careful protection against cracking. PVDF is more forgiving, but its output is limited. Both materials, when embedded in concrete, can harvest vibration energy in the milliwatt to watt range per device. Scaling up to a megastructure means thousands or even millions of these tiny harvesters working in concert, each capturing a sliver of the energy unleashed by the Earth's motion. On the shores of Lake Constance in southern Germany, engineers at the Fraunhofer Institute rolled a concrete sphere nearly 30 feet across into the water. At first glance, it looked more like an art installation than a battery. Inside, a simple idea took shape: use the weight of water and the strength of concrete to store energy, not in chemicals, but in pure mechanical force. They called it STENSEE, stored energy in the sea. The prototype, weighing nearly 400 tons, was anchored at a depth of over 600 meters, where water pressure alone could crush a submarine hull. When the grid had surplus power, pumps forced water out of the hollow sphere, creating a vacuum. Later, when electricity was needed, a valve opened, seawater rushed in, and the pressure spun a turbine, generating electricity. The first test delivered a capacity of 0.4 megawatt hours, with a target output of half a megawatt per sphere, enough to supply a typical home for weeks. The vision did not stop at a single sphere. Lead engineers imagined entire fields of these concrete batteries, scattered across the ocean floor, each one storing and releasing energy on command. The numbers added up fast. Fraunhofer simulations suggested a global potential of over 800,000 gigawatt hours, enough to power 75 million homes for a year. The Stensea project proved that concrete is not just for dams and bridges. It can be the backbone of a new kind of energy storage, one that is mechanical, modular, and built from the simplest materials on Earth. For advocates of seismic energy capture, this was more than an experiment. It was a working proof that concrete structures can do more than resist the forces of nature. They can harness them. A 328-foot concrete dam faces a brutal test every time the ground moves. For engineers, the challenge is not just surviving the quake, but using it. In the lab, piezoelectric modules embedded in concrete can handle millions of stress cycles before their output drops, far more than the number of major quakes any dam will see in decades. But the numbers tell a different story about scale. Even with aggressive designs, the total energy a dam can capture from a magnitude 7.0 earthquake rarely exceeds a few kilowatt hours per event. That's enough to run emergency lights or sensors, not a city. While peak output during shaking can spike into the hundreds of kilowatts for a few seconds, the average power over a year settles in the single-digit watts range. The audit is clear. Concrete and piezo materials are durable, but the energy budget remains modest. For now, the real value is in resilience, not revolution. California's seismic planners watch the San Andreas Fault with a wary eye. The last major rupture, simulated at magnitude 7.8, projected more than $200 billion in economic losses, most of it from power outages and destroyed infrastructure. For them, any technology that can both absorb seismic shocks and keep the grid alive is more than an experiment. It is a potential safeguard for millions. Across the world, Turkish engineers face a different urgency. The 2023 earthquakes left tens of thousands dead and entire cities in ruins. As reconstruction begins, proposals for resilient infrastructure and smart energy systems are gaining traction, with some advocates pointing to the promise of seismic-powered dams. The economic case is hard to ignore. If advanced earthquake harvesting structures could trim just 10% from the cost of a major disaster, the avoided losses across California and Turkey alone could approach $50 billion. For policymakers, the draw is not just clean energy. It is a shot at long-term resilience, a way to turn nature's threat into a public asset. Seismic energy still slips through our fingers, but each breakthrough brings the idea of earthquake-powered cities closer. As urban populations grow and disasters intensify, the race to capture untapped forces becomes urgent. The future belongs to those who refuse to waste the world's hidden power. What would you build?